Welcome to my master's thesis defense. Yeah, I'm right there. Okay. And my project was related to the cosmological constant problem, or my more catchy title, the cosmological calculation conundrum. So let's get started on the background information. So we already know that there's a universe here. And something about the universe is that it keeps expanding and the rate of its expansion is itself increasing. How's that happening? That's what my research is going to try to address. So I'm going to begin by going through some background information, starting with Einstein, then redshift measurements and supernova measurements to today. Going to talk about this cosmological constant I've mentioned, and get into some quantum fields. We're going to talk about some math, and then we'll talk about the data that I actually generated with Doppler prior supervision. Okay, so let's get started with Einstein, as all modern physics talks seem to start. So in 1915, he wrote out his field equation, all mu nu minus 1/2 g nu v, all equals negative 8 pi g t mu nu. So Einstein looked at this equation and he realized that it predicted that the universe was either increasing or decreasing in size. But at this time, Einstein and most physicists assumed that the universe was static, as you can tell because he had a thought bubble above him saying just that. So, to reconcile this with his belief, he slapped in a new constant we call the cosmological constant lambda. Well, this will basically provide some type of energy to space such that the universe did not increase or decrease in size but stayed static, like his belief of the universe behavior was. Okay, that's all well and good, but then observational astronomers throughout the 1910s and 1920s starting to do...
Is there a way to minimize the pictures over there?
Yeah, I can do that.
Okay.
A second.
Yes, out of the way completely. Much out of the way is it?
Okay, like that. Just shove it
There you
down.
go. There you go.
Okay. Yes. Okay. So in 1910s and 1920s, a bunch of astronomers started measuring that light from stars was overgoing a redshift overall. There was some blue shift. What this means is that if a source emitting light is moving away from the source absorbing light, the frequency at least the light appears to be emitted gets elongated, the wavelength elongates, and the light gets more towards the red side of the electromagnetic spectrum. On the other hand, if you're moving closer, you can see that's as if the light's getting emitted more frequently and looks like the wavelength gets squished up and you get blue shift. Overall, most stars will get redshifted. Okay, it could be that a bunch of stars are just randomly moving about. Well, Hubble in 1929, I believe it was, started to actually look at the amount of redshift and compare it to the distance of the star. And he saw there was a direct correlation between the distance away from Earth and the amount of redshift, which implied that the movement was not entirely random, but that the stars were moving away from us in general because the universe itself is increasing in size. So the universe should be expanding. Well, that means the universe is static, and Einstein took away the cosmological constant because the equation, as it was, predicted that the universe would change size one way or the other. Okay, and that's largely how things stayed throughout most of the 1900s until we get to 1998 when some measurements occurred. So, there were two independent international astronomical collaborations, the Supernova Cosmology Project and the High C supernova search team. And what they were doing was measuring the light emitted from type 1a supernova. Well, a supernova is when a star explodes, and this animation shows that explosion is quite bright. And if for the conditions for a star to go nova are very precise, so we know how luminous this should appear. If you see how luminous something is absorbed compared to how luminous it should be, you can get a graph at how far away the object was. And furthermore, all supernovas, type 1a supernovas, should emit a specific spectrum. The spectra corresponds to the chemical composition of the star. Stars initially at the start of the universe, when they first start being formed in population 1, will have been mainly formed of hydrogen and maybe some helium, while newer stars have access to heavier elements. So if we're looking at type 1a supernova, these supernova can be found in the oldest galaxies, as well as some of the newer ones. So now we have events of some standard luminosity we should know. We refer to as a standard candle. And if you look at a bunch of supernovae at different distances and take measurements of the luminosity and the amount of redshift, you can get details about distance and the expansion. What these measurements found was that the rate of the universe was increasing at an ever-increasing rate. Well, you do some math, and they found that this corresponded to a universe that has some energy out in the vacuum of space, energy density, of about 10 to the negative 8 ergs per centimeter cube. Okay, so the equation needed to be fixed. Einstein's field equation predicted that the universe was expanding or decreasing, but not at an ever-increasing rate. For there to be an ever-increasing rate of expansion, there actually does need to be some added energy into space corresponding to the cosmological constant, which could be related to the cosmological constant, that could be related to the energy density by the energy density of the vacuum is equal to the cosmological constant over 8 pi g. So this constant's not zero. Next thing you want to do is see if you can calculate this value theoretically and agree with observations. So where does the energy come from? One candidate for the energy source are the random fluctuations of quantum fields. So just quickly jump into quantum field theory. Classically, we see particles as balls with fixed positions and momentum, but if you go to quantum mechanics, you find that particles are described by probabilistic wave functions, and then in quantum field theory, particles are now described as originating from these fields that permeate all of space. Now, in the lowest ground state of these fields, there's always going to be some random fluctuations that contribute some energy to the space they're inhabiting. Okay, so in particular, we categorize particles as being either, either being bosons or fermions. A boson is a particle with integer spin and is symmetric under exchange, while a fermion is a particle with half integer spin and anti-symmetric under exchange. Okay, so the quantum fields happen to be described by very similar mechanisms as a harmonic oscillator from quantum mechanics. So if we look at the harmonic oscillator Hamiltonian, that gives you a kinetic tone plus 1/2 m omega square x square, which is just your potential of being in a harmonic oscillator. If you look at Schrödinger's equation, h psi equals e psi, we can plug this in and get this big equation. So now we're going to want to massage this equation for reasons that will appear in a bit. So I'm going to define some new big operators x and big X and big P to replace the x's and the ddx's and get rid of the messy constants. So if you make that substitution, you can now write the Hamiltonian to be x squared plus p squared, and then we can factor this out using complex i's to get x plus ip at x minus ip, which are customarily defined as x plus ip over root 2 is a hat, which is called the annihilation operator, and x minus ip over the square root of 2 is called a hat dagger, the creation operator. These operators, a and a dagger, when they act on a eigenstate of a wave in a harmonic oscillator, they raise the energy level or lower the energy level. So a dagger ends up raising the energy state while a lowers the energy state. We'll get to what this corresponds to quantum field theory in a bit. So in quantum field theory, we use these A's, A daggers, which have a commutation relationship of A comma A dagger equals 1 to describe bosonic quantum fields. So using A dagger, we can rewrite X and P in terms of them, which implies that the Hamiltonian can now be written as half H bar omega A dagger plus A dagger A. Use the commutation relationship to do another substitution. And we get H bar omega over 2 equals 2 A dagger A plus 1. Let's do another substitution. Let's simplify this by carrying out the 1/2. And here we have the Hamiltonian for bosonic fields, particles. Well, there's a substitution where A dagger A quantum mechanics is called the number operator. So big N is another eigen, it's another operator, which is equal to A dagger A. So we look at our number operator. If this acts on some eigenstate n, it will return some eigenvalue n as well. If h is a function of the number operator, that means that it's also an eigenfunction of little n, which means when it acts on little n, we now get h bar omega little n plus half times the original eigenfunction, eigenvector. Okay. Well, this now gives us the eigenenergies of our harmonic oscillator for a boson, and particularly if we want the ground state, we just say that's when n equals 0, we get h bar omega over 2 is the ground state energy contribution from a boson. Now in quantum field theory, by analogy, there's a similar equation where we now use B for the creation and annihilation operators for fermions, but instead of adding them together, there's a subtraction. You could go through the same math, but now you have an anti-commutation relationship equaling 1. If you go through the same math, you can show that we get a new equation, h bar omega, the number operator minus 1/2, which by the same method as before, you get your eigenenergies. And now the ground state energy for fermions, when n equals 0, is negative h bar omega over 2. So the bosons contribute positively in the ground state, and fermions contribute negatively. So if we look at a field in quantum field theory, just picture some wave out there in space, not really, but in the ground state, you just have empty space. When you go to state 1, you now have an excitation of this wave field, which is a particle, 2 corresponds to 2 particles now in space. In quantum field theory, the A daggers at A's create and destroy particles. So A dagger adds a particle to the vacuum, and A by itself removes particles. Okay, so we'll want to find the total energy contributed to the vacuum from these quantum fields. So as we said, everything should be in its ground state, so we get positive contributions from the bosons, negative contributions from the fermions. Now let's look at omega. So the frequency in the harmonic oscillator turns out to be a function of the mass of the particles, as well as k, which is a wave vector. The wave vector relates to the momentum via momentum vectors equal to h bar wave vector k. Okay, so for a particular particle, they have some known fixed mass, but we could have many different wave vectors and many different momentums. So, if we want the total ground energy, we need to sum over all of the energy contributions. Talk about that math in a minute, for all of the masses and all of the possible k values. When this is traditionally done, you get a value of 10 to the 112 ergs per centimeter cube, not squared. Well, so there's energy density predicted by theory. Unfortunately, that does not really agree with observation. It differs by 120 orders of magnitude. So this is the problem here. We have a very big disagreement between the theoretical values and the observed values. So either the observations are inaccurate or the theory is inaccurate. Well, we believe that it's more likely the theory is incomplete. So here's why. When you do that calculation traditionally, they're using the standard model of elementary particles. Well, one possibility is this model could be incomplete. We don't know all. There might be particles we don't know of yet, such as dark matter candidates. And furthermore, some of these particles, such as quarks, do not exist in isolation by themselves at low energies. In fact, quarks like to form a composite particle, which is a proton, which does exist out in space. The quarks, to be by themselves, need to be at really, really high energies. So perhaps we also need to consider a bunch of composite particles when doing this calculation. So let's look at calculation. So we have our bosonic ground states, the fermionic ground states. If we want the total energy density, it comes from this energy density equation, where the -1 to the 2Sn factor. Sn is the spin of a particle. If you're a boson, your spin is an integer. So 2 times an integer is going to be an even number. -1 to the even number is going to be 1. You get a positive contribution. Fermions are half integers. Half integer times 2 gives you an odd number. So the -1 to that power is still -1. Negative contribution from fermions. Gn stands for degeneracy of the particle, such as photons can be polarized in 2 different modes. So there's 2 ways you can have a photon. Electrons, other particles have different spins up and down. There's a lot of different degeneracies. Then h bar omega over 2 comes from the ground state energies. However, as we said, omega is a function of the wave vector. There's many different possible wave vectors, so you need to integrate over all of k space. So if you do that, firstly, if you don't give a boundary to this integral, it's going to go up to infinity. Well, we don't want infinite vacuum energy, so you need to define some maximum k value, k max, when you do this integral. And traditionally, the maximum k corresponds to the Planck scale, because at energy ranges above the Planck scale, our knowledge of physics is incomplete, so we can't jump to that region because we would be inaccurately describing it. So we limit it to the physics we do understand. If you do the integral for k-space, one way to do it is convert into spherical coordinates. So dk cubed is dk for the radial component, then k d theta for the theta component, and k sine theta d phi for the psi component. There's no angle dependency, so you just pick up a 4 pi, and this leaves you with the integral of m squared plus k squared, square root thereof, all times k squared, which can be integrated and expanded to this, the animation's out photo, to this long equation, which a physicist in 1951, Pauli, looked at this equation and said, well, we could set this energy density to 0. Back in 1951, this was before the supernova type 1a measurement, so it was still thought that the universe was static. He looked at the equation and came up with 4 conditions that had to be constrained. Firstly, you need the same number of, well, these first 3 equations to constrain the energy to a finite energy. Firstly, you need equal numbers of fermionic degrees of freedom and bosonic degrees of freedom. So for every k to the 4th over 4 term from the bosons, you get one from the fermions. Positives, negative contributions cancel. Similarly, we need the m squared contributions to be the same and the m to the 4ths to be the same to constrain the energy. Finally, there's one more condition. M to the 4th natural log m squared is needed to exactly set the energy density to 0. We now know that the energy density is not 0, so we will not be using this equation when we look at our model. So, using the first 3 conditions is the backbone of the code that Dr. Prado and I have worked on, where we are going to try to find ways to calculate finite positive vacuum energies. But instead of using the standard model, we're going to be using a bunch of random particles, masses, because we don't know the physics of how to get the unknown particle masses that we may have not measured yet, and composite particles, by adapting a method from nuclear physics called random matrix theory. Now, in nuclear physics, you have nucleuses, which are very complicated composite particles with a bunch of protons and neutrons, all will add up to some all with different quantum numbers. And in nuclear physics, you can have different energy levels or excited states for your nucleuses. Now, it turns out that the physics to calculate that level spacing is very complicated. You can forego rigorous calculations by adapting something called random matrix theory, which is basically an analogy to statistical mechanics, where instead of just using one variable to simplify a bunch of complicated mess of equations, you have a matrix where you randomly assign values to this matrix. Well, furthermore, in nuclear physics, they found that the energy levels for individual exciting nucleons follow this distribution P W of t equals pi over 2 t e to the negative pi over 4t squared dt. Where this basically looks like a Rayleigh distribution suggested by Wingle for the probability of having different energy levels. Now, it turns out if you have a bunch of independent particles with their own quantum numbers, they're going to have their own individual energy level spacings, which is something we're going to be looking at here, where we have a bunch of independent particles. If you add these energy levels together, they now, from the different particles, and you combine them, you get something that looks like a Poisson distribution that looks somewhat exponential. So
could you
yes.
say what T is?
T is the, is it a unitless quantity that is used to measure the distance between the energy levels? I don't remember the meaning of T off the top of my head, but I do have the textbook.
What? It's spacing.
What? Unitless spacing between them.
Yeah, but yeah, I mean, unitless, yes, but it's proportional to the spacing.
Right.
That's all I know, yeah.
Okay. Yes. So if you just have one particle and its spacings are going to be defined by this blue graph, where you're unlikely to have levels right on top of each other. But if you add a bunch of independent particles levels up, there's no reason for levels to not now go near each other for independent particles, and this results in the Poisson distribution that you could also think of as being exponential, the red graph. So, in our code, we're going to take Pauli's three conditions, simplify them, and generate random axes using an exponential distribution based on the success of random matrix theory in nuclear physics. So now, the conditions we're using is that the number of fermions equals the number of bosons. We're foregoing degeneracies for now to just get very simplified to look at, have more control over what's going on, and does it correspond to reality anymore, except for the fact that of our boson masses, we will always have a mass equal to 0. This is due because experimentally, we know the photon has 0 mass. So there's one boson out there with 0 mass. Theoretically, the graviton, which hasn't been confirmed, would also have 0 mass as a boson. And furthermore, now if we're going to degeneracies, the mass square sum of the fermions should add up to be the same thing as the mass square sum for the bosons. Same for the mass to the fourths. Okay, so we write a code that will begin by creating a list of n particles. Well, half of them are bosons, half are fermions. One boson always has 0 mass. The fermions masses are randomly initialized. And when you initialize the further masses, so boson 2, fermion 2, how you define it is by saying it's equal to the mass of the previous particle plus a random number generated by an exponential. This way the initial mass spacing follows a exponential. Now these masses are going to be optimized in a minimization function where we're trying to minimize the m squares at m to the 4th conditions, where we want the m square minus m mass boson square minus the mass of the fermion square sum to go to 0, as well as the mass to the 4th bosons minus mass to the 4th fermions to go to 0. When this is done, you get a perfect optimization that should go to 0. We define the sum as being 1 plus those differences because in minimization schemes, the success of the minimization is defined by some relative error from the absolute minimum. If the absolute minimum happens to be 0, the relative error is ill-defined, so we just pick a constant for the relative error to be measured with respect to. So 1.
Is there a reason why you have the two terms there, the squares and the 4th powers, or?
It's always been like that, I don't remember.
I'm trying to understand.
Why we're squaring.
And why, you've got the two, I mean, I can imagine just take 1 plus the sum of the squares and do like a least squares. This is, what's the motivation for the second term?
The mass to the fourth.
Yeah.
That comes from, how do I go backwards?
I missed that, let's see.
Yeah, third line.
Yeah. If we go to
Oh, that's from,
Pauli's equilibrium conditions, we have a mass square we want to get rid of, and we have a mass to the fourth
okay,
term.
Actually, it's really the mass fourth log
Log.
k.
in the log term, okay.
Because the log k max will diverge, so
Mhm.
the mass of the fourth has to sum to 0.
Yeah. So when we do the sum, we have mass squared, so mass to the fourth. So we then calculate the energy density from these minimized masses if the optimization is successful by having an error less than a defined threshold. If you're unable to minimize the sum to an acceptable value, we do not save the optimized masses. Okay. And then you repeat this a specified number of times where you manually generate multiple spectrums of n particles to gather greater statistics. Okay, but before we do many particles, let's see if the code can actually find solutions. So in that sense, we want the mass squared sum for bosons to equal the mass squared for fermions, which should both equal some, we could say, constant value. Similarly, you can do this for the mass to the fourths, equals some other constant. Okay, so to check to see if the optimization can find solutions, hold one of these collections of particles constant. So for example, hold the fermions constant. So you randomly generate them, and now we want to see if we can find bosons that satisfy these conditions. If we make a substitution of xi equal nbi squared, we now get two equations that the sum of xn equals some constant c1, and the sum of xn squared equals the constant c2, which c1 and c2 are defined by the fermionic masses. Well, the first equation here just defines a plane or a hyperplane in n dimensions, and the second equation defines a sphere or a hypersphere in n dimensions. So our solution to this system of equations should correspond to the intersection of a hyperplane with a hypersphere, or with 3 dimensions, a plane with a sphere. So we did some test runs where we had free masses for the bosons. One of the mass bosons was always 0. So we have 3 additional free masses. Then we have 4 fermion masses. We held 1 fermion mass at 1 and had 3 fermion masses in addition to that. And if you look at the 3 boson intersection, solution is a ring or a circle which should correspond to the intersection of a plane with a sphere. Okay, the code was able to successfully find optimized masses to satisfy this simple condition. Now we could do trials of higher particle numbers and dimensions our human brains can't visualize. Okay, also just saying, we do initialize stuff using an exponential distribution, which is the red curve, and blue is the initial mass spacings for the bosons for a trial with 20 particles. After we optimize these, the green curve is fit into the optimized data, the orange dots, which can still be fitted by an exponential, not quite as well, but it still has this form shape roughly corresponding to an exponential. Okay, so we did trial runs for totals of 12 particles, 20 particles, 50, 100, and 200, and looked at statistics. of them. So one of the things we looked at was the spacing statistics, which the optimized spacing should still look like exponential. These Y graphs here have log scales. And what we found is that the lower particle numbers fall off quicker than higher particle numbers, as in if you have more particles, there seem to be more chances for your spacing to be bigger, and these distributions will attain larger values, up to 300 sometimes. We cut the graphs off to make it easier to see. Overall, the lower particles do drop off sooner, except the 200 total particles, the spacing tends to be below the 100 and the 50. If you look at the lowest free mass of the particles, so the fermion free mass is the first fermion mass, the lowest free boson mass is the second lowest boson mass, the lowest is always 0. Have some interesting statistics. The fermions, I'm pointing for the people here, but the people, I'm just move my mouse. So let's see, am I able to?
That's the table.
There we go. Okay. So, for lower particles, the lowest free fermion, initially the frequency tends to be most likely to occur around 10 to the 0 to 10 to the square, 10 to the second for the lowest mass. And as you increase the particle numbers, this frequency drop around unity tends to decrease. But the fermions but as you increase, the lowest mass being around 10 to the negative 15th increases with the frequency of this occurring increases with the particle number. So as this slope goes down with number of particles, the much lower mass possibilities increase in frequency for fermions. Now the lowest free boson, on the other hand, has some different behavior, where initially the lowest free boson tends to also be around 10 to the 0, 10 squared, but as the particle number increases, the frequency over here does still decrease, but now you have increased frequencies at greater mass values away from 0. So while the fermions tend to go towards 0 mass with more particles, the freest boson, the lowest free boson mass tends to drift away. Which is interesting. If we look at the medians of these distributions, after you reach about 50 particles for both bosons and fermions, the median mass space tends to remain relatively constant. My thought is that 12 masses is rather low, it's less particles than there are the standard model, so to get reasonable statistics it might just need to reach some minimum and then some maximum, some minimum value for this to flatline was my initial interpretation. And the lowest mass for both lowest free mass for both does increase with particle number. Do mention that for bosons this goes from about 1 to 30, so this increases by a factor of about 15, 2 to 30. But the fermions, this graph scale here is 10 to the negative 7. So the median free fermion mass tends to be much smaller. It does tend to increase. However, you start at around 1 and you go to around 2, so it does not increase by the same factor, a much less so factor than the bosons. Okay, now if we look at the energies of our optimized masses, The range, so this is a symmetric log plot, so 10 to the 0, 10, 1, 10 squared, 10 to negative 10 to the 0, negative 10 to the 1, negative 10 squared. So it's not a log plot, it's a symmetric log on the x scale. When you look at the statistics for the energies, the range of energy values increases by orders of magnitude as you increase the particle number. However, if we look at the average, the median energy, it does increase with the number of particles, but it's always positive. So the median is always positive, which suggests that the positive energy, positive vacuum energies are more likely to be computed with this model than negative, which is good because, well, we know the vacuum energy density is a positive. Furthermore, we have these color 2D histograms here where we look at the vacuum energy, log thereof, and the lowest free mass for both. The bosons, so on the right we have positive energy statistics. On the left, we separate out the masses that correspond to negative energy. We don't graph them in the same plot because you can't take the log of a negative value, but we still want to see if there's different statistics leading towards positive or negative energies. The fermion masses for 12, 50, we also have 100, 200 particles, all tend to cluster around -8 when you take the log. Well, the bosons cluster between 0 and 2. This is true except for the lowest number of free particles at 12. When you go to the negative energies, there's overlap between the fermions and the bosons. Again, this might just be because this is such a low number of particles that it can't really be extrapolated to model what's going on. But for all of the higher number of particles, you don't get those overlaps. Also the density here, the amount of negative energies was a lot low counts. The densities are lower for negative than positive, so you might also just not have enough statistics with the number of trials we did for the negative energies from 12. Negative energy densities from 12 masses. And you can also see from these plots that the peak and the median energy, you can also see where it's the most densest increases in Y value as the number of particles increases. 5, 6.5, 7. Okay. So some general trends from our data is that it seems that positive energies are more likely than negative energies. The fermion lowest mass goes towards 0 as you increase the number of particles. While the boson lowest free mass drifts away from 0 as you increase the number of particles. So future work in this research would be to fill in the statistics by doing trials for a lot more different total number of particles to see if this can give us better insight on the behavior and the statistics from that. And also you'll gradually want to actually work in observable physics into the code. Right now we just have the one boson mass that's 0. One thing you want to eventually add in is degeneracies, as well as possibly other masses from the standard model. I want to thank all of my friends from Iowa who've helped me stay sane during my master's degree, in addition to my advisor, Dr. Carroll, who's right here. I don't have a picture with him. Any questions?
Okay, so usually take questions from the audience first, and then the committee.
David's clapping.
Yes. Do you have any idea where in with this exponential distribution, what the standard model look like?
So the standard model has one set of masses. All of our graphs right here are averages of many different masses for the total number. So I don't know if it makes sense to make a comparison from a statistics to one data point file.
Where it's showing with respect to the lowest mass.
Well, the lowest fermion masses are known. Well, they're roughly known.
Yes.
The neutrino.
You know, they're neutrinos, and you have a rough idea of where they are.
All right.
But beyond that,
How well?
I mean, that would be another approach, to go through the particle data group table and just add everything up to some energy.
And just see how it fits,
Yeah.
where that data point would fit onto the plots.
Yeah. And one of the really remarkable coincidences, and what part motivates this, is that the neutrino mass, the lowest neutrino mass, is supposed to be in the neighborhood of 10 to the minus 3 electron volts, and the vacuum energy is 10 to the minus 3 electron volts quantity to the fourth. They're very close to each other,
Yeah.
especially when you're talking about 100 orders of magnitude.
Yeah.
There's this very odd coincidence
Yeah.
that the lowest known non-zero mass happens to agree.
Can you explain how this stuff scales with particle number? I didn't completely follow that.
Yeah. So if I reopen the PowerPoint, am I still showing?
Is there some normalization?
Yes, I was just trying to
here?
share the screen, so. Yeah, so the,
It should flatten out at some point. There should be some asymptotic.
yeah, so the spacing, so the median spacing tends to flatten out when you increase the number of particles, but the lowest free mass median tends to increase with the number of particles. The bosons increase to a greater amount. You go from about 2 to 30, but this is about 1 times 10 to the negative 7 to 2 times 10 to the negative 7.
I'm trying to understand how the vacuum energy itself just scales, you know what I mean?
So,
Can't see the screen, can you?
yeah, okay. How do I escape? Let's share screen again. Share. Okay. So if we go there. So
This is the number of types of particles as opposed to the total number of particles. Is that how I should understand
this
it?
is the total number of particles on the x-axis. And this is the median energy density calculated.
Oh, it's the energy density given that number of particles. So,
Yeah,
Median.
median.
yeah, okay, so okay, sorry.
Mhm.
Now I understand.
And this is a histogram of the frequency of different energy densities color-coded by number of particles.
As the number goes up, that thing should eventually level off somehow.
It might go infinite.
Or it just grows.
It just grows.
It might grow up to some cutoff.
Uh-huh.
We're currently doing more simulations with different particle numbers.
What's the interpretation if it keeps growing in terms of the, the energy
Well,
density?
There probably would there'd probably be a cutoff where this model would break down.
Okay.
And so, this is very much a toy model. There's some upper cutoff, definitely, but there's probably also lower cutoff, because if you look at the low masses, the standard model, those aren't very well described by a random matrix model. They're not very random. So they're probably both IR and UV cutoffs. And this, a realistic version of this would probably be for something in the middle, where you're dealing with all the mesons and baryons.
And particles count if they have a certain lifetime in this compared to the age of the universe, or?
That's a very good question. I'm not sure about that.
Protons you want to count, probably.
Absolutely, yeah. Even neutrons, probably.
And neutrons and so.
I mean, there are good arguments that the lifetime shouldn't matter, but certainly if the lifetime's short enough, that doesn't seem quite right.
Yeah.
So, I mean, the way to really test this would be to have a lattice model that had bound states in it, and to be able to actually numerically compute the vacuum stress energy tensor, and then also be able to compute the low energy effective field theory states, the bound states, and see if those really match. Because this is something of a, it's postulate.
Sure.
That one has to check.
Any other audience questions?
So,
Let's see, am I audience or?
well, we can just
I asked the question, so go ahead.
Yeah.
Let's see, is it really possible to get the thesis, the document? I have a question about some equation.
I have a printed out copy. Yeah.
So, let's see, but then you don't have it on your computer, right?
Oh, I can pull it up. Well,
While you're on that thing, you can log on to both.
You can share.
You can log
yeah.
on to both.
Give me a moment to do that.
Yeah.
So stop sharing.
At the top of the screen in red.
Oh, stop share. And then I can join and share. Okay, then share screen.
Actually, I think we're supposed to have just the committee at this point. So if there aren't any general questions and there's specific questions, then we should do that in a breakout room. So that's supposed to work.
Really quick, Jonathan, I had a quick question.
Okay.
That yeah, maybe I should have asked this right at the beginning of the question session, but I think I missed it. But I wanted to just get your conclusion. Like, what do your results say about, or predict, or talk about the cosmological constant conundrum?
Well, our results seem to say that if you go about using a random approach, you can calculate energies that are energy densities that tend to be positive versus negative, which seems to suggest that if you eventually add in more physics, this type of approach may be a possible way to attack the problem. We haven't so much gotten insight in the problem other than see if we can develop a new method to tackle the problem, because people have been working on this problem since 1998 and there still has not been much progress.
Okay, I see. So I guess what you're saying is that, well, I remember that you said in your next steps is to kind of put more physics into your equations, basically. Mm-hmm. So what you're saying is that this very preliminary toy model, at the very least, points in the right direction.
Yes. Will you agree
Okay.
with that?
Cool.
Am I allowed to point out something I note in the figure when it has the frequency of versus the vacuum density?
Yeah, give me 1 second to pull that back up. Share screen, PowerPoint.
Right there.
Yeah.
As you add more particles, it gets closer to 0, and so
Okay, so gets close. Okay, because this is a histogram,
it becomes more probable that it.
well, it's not so much that it's approaching 0 frequency, but you now have a bigger range of values you can have. So the frequency of
Oh, okay.
your other values,
And mixed up the blue and the purple.
yeah. Yes, blue is the lowest number and purple is the biggest number.
Okay.
Okay. Yeah. Any more questions or critiques? I don't know where to look.
Let's go to the breakout.
Okay. Yeah.
Or kick everyone, that's not.
Well,
You
we
never
don't
know.
want to kick people out because. So we're supposed to ask questions
Go to the top
of
of the
the
screen.
candidate in private.